Hi everyone, my name is Kai Shung Yang. I'm going to present homework number 2. For this homework, we are going to do code implementation and write application to demonstrate the code with Iris dataset. For the code implementation, we primarily to implement the cost functions, acceleration functions, regularization terms to cost functions, and job array on the provided neural network source file. The first part we're going to do is to implement the cost functions. Before we jump into the code, we first take a look at the standard equation of the cost functions. As we see in this table, there are three types of cost functions, which are quadratic, cost entropy, and log likelihood. There are conditions applied to derivatives. For the cost entropies, we assign the 0 to the derivative if the activation value is 0 or 1 in order to avoid the 0 denominator. For the log likelihood, we only count for the corresponding activation value if its target value equals to 1. And assign 0 to the derivative if corresponding activation value of the target label is 0 in order to avoid the 0 denominator as well. Next, take a look at the code. Here is the cost function class which is provided in the source code. The first one is the quadratic cost which is provided, and the second one is the cost entropy cost function. The top function is the main cost function, and the second one is the derivative function which we need to implement the code. As I mentioned that the derivative value assigned to 0 if the activation value equals to 0 or 1. If not the case, then we just use this formula to get the derivative value and then returns the vector. The third cost function is the log likelihood. Since we only count the corresponding activation value if its target value equals to 1, so that we first search out the max index of y and then find the corresponding activation value and take a log of it and then return the scalar. For the derivative, since we need to return the vector, so we initialize the vector value 0 away and then search out the max index y and then find the corresponding activation value and then calculate the entire derivative, and then we place the index in the 0 away with this derivative value and returns the vector to the caller function. If the activation value equals to 0, then we just return the entire 0 away vector. Let's take a look at the activation function. Here are four types of activation functions: sigmoid, tangent, value, and softmax. This column shows the activation functions, and this column shows the primer of the activation function. C is the output of the linear function. Let's take a look at the code. Here is the code for the activation functions. In terms of implementation, we use the class method for the derivative functions because we want to get the return value directly from the main fn functions. As you see here, we basically pass the class parameters and the C parameters to the main fn functions and then get the return value from the fn functions and use that value to calculate the derivative. That basically applies to all activation functions class. The sigmoid, tangent, and value class are basically built based on the equations that I showed before, and the softmax is a little different. We replace the C value by using the C minus the max C value for the numerator and denominator because we want to avoid the situations like infinity and makes the output more stable. The derivative of the softmax is provided in the source code and also built based on the equation that I showed before. Now let's take a look at the rules that apply on the activation functions for the hidden layer and the output layer. Here is the rules applied on the activation functions. I made some screenshots out of the code to make it easier to discuss. The first one is in the backprop function, we rescale the activation values in 0-1 scale if the hidden activation function is tangent function and its cost function is not quadratic. This is the code. And the second is in the set parameters functions, we override the activation output functions to sigmoid if the activation output function is tangent and its cost function is not quadratic. And the third one is in the set parameters function, we override the activation function of the hidden layer to sigmoid function if the activation hidden function is softmax. That basically means that softmax is only applied in the output layer. And the fourth one is in the set parameters function, we override the cost function to log likelihood when the activation output function is softmax. That's all the rules applies on the activation functions. Now let's take a look of the regularization parameter settings. The regularization parameter settings, there are two types of regularization, L1 and L2. This is the regularization terms and this is the regularization prime terms. In the update mini batch functions, we implement the prime of regularization terms to adjust the weights and the bias for every mini batch. If specify L2, then this term is used to adjust the weight and the bias as well. And if specify L1 as the parameters, then we use this to adjust the weight. But for L1, the bias adjustment is ignored. If there's no regularization terms is specified, then you just use the regular adjustment terms for the weight and bias adjustment. In the total cost functions, we add the regularization terms to on top of the cost functions. As you see here, the big difference between L1 and L2 is L1 takes the absolute value of W, and L2 is the square of W. As shown here, L1 is the absolute value of W and take a summation, and L2 is the square of the W and take the summation. That's it for the regularization parameter settings. Let's take a look of the dropout settings. Here is the dropout code implementation. We first need to add new parameters to the network class, and then in the update mini batch functions, we generate the dropout mask based on the number of hidden layer and number of loops in the hidden layer by using the random binomial functions. And then in the pepper functions, we implement the statements to calculate the new activation function based on the dropout mask. As you see here, if the dropout percentage is set larger than 0, then the activation value will times the dropout mask to get the new activation values. Here's the example. If the dropout mask is equal to that and the activation value is equal to that, the activation times the dropout mask will get the new activation values. As you see here, the first term is equal to 0 because the dropout mask is equal to 0. That's it for the presentation. Thank you for watching.